Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 7 for the course of Communication Technology. My name is Engineer Jaffar and I am your instructor for this course. So, you all know that in the last lecture we have discussed about the amplitude modulation, and we have also done quite of the numericals of that topic regarding the amplitude modulation, that how that amplitude modulation is done and how these parameters are being varied. Now, after the completion of the numerical portion, we are going towards the type of the amplitude modulation. That what are the different categories that we can use while using an amplitude modulation. So there are several categories, but out of that several categories, I'm going to explain you these three categories. The first one is a double sideband, or commonly known as DSB with suppressed carrier. Also, there is another type that is known as single sideband or SSB, and the last one is VSB, or commonly known as vestigial sideband. So these three will be our today's topic, that how we will use these types in when talking about amplitude modulation. So just to let you know, just in the beginning, you should know that AM, that is amplitude modulation, double sideband, single sideband, and vestigial sideband, these all are the subclasses of amplitude modulation, because the message that is basically transmitted or transferred is basically dependent on the amplitude of the message signal. You know that in amplitude modulation, the output of the modulator is basically varied as compared to the input of the message signal, or the amplitude of the message signal. So this is the basic introduction of all these topics, or these subheadings of types of amplitude modulation. Most of the time, this AM basically means conventional AM or standard AM, or you should also know that this AM is also referred as double sideband with carrier. The first type is a double sideband with carrier. This is the alternate name or synonym of amplitude modulation. So these are the two types of this double sideband. The first one is conventional AM, that is with carrier. This is the first one, that is conventional AM. This is also known as DSB. DSB, but this is with carrier. And the second one is double sideband with carrier suppressed. So CS DSB or DSB-SC, or simply DSB. So this is with the carrier suppressed. Now, what I'm talking about the suppressed carrier. So before going to that, you should recall that conventional AM, which we did in the last lectures actually. So this is the equation for the equation for the amplitude modulation, and if you recall that this was the complete equation in which there was one upper sideband and the lower sideband. And if I show you in the diagram, you can see that this was the scenario. This was the upper sideband, this was the lower sideband, and in between there was a carrier which is also involved. So this was double sideband with carrier, or also known as conventional AM. If you recall this equation, you might get this type of frequency spectrum, or spectrum of the signal. So this is double sideband but with carrier, because you can see that the carrier is in the middle. So this is the double sideband with carrier. Now there was a lot of issues that were coming into the AM. The most importantly was the more of the energy consumption. You know that the energy consumption was very high in the amplitude modulation or double sideband with carrier. So the main portion of that energy was going towards the carrier. Most of the power were getting lost in the carrier transfer, and we also reduced that 80 to 90%. And in one case, there was a numerical in which the loss of the power that could be saved was 94%. So it was a huge, humongous amount of the energy loss. So which we want to nullify. So for that reason, we are going towards the first type, that is known as double sideband with suppressed carrier. So this is all the previous equations that we also used in the numerical portion as well. Now this is the single sideband with carrier suppressed equation. If you want to see that how does it this we get this equation from the double sideband, so it is nothing that much difficult. You have just applied a simple frequency band filter. So you have rejected a frequency and you have accepted one frequency. So you can see over here that there is no portion that is only involving the carrier. This is only one term, and this one term is basically the only term basically which do not have any kind of carrier involved except the frequency, but there is no individual term of that carrier equation. So how do we get this equation? So basically this is the derivation, and this is also already done in this on your book that is provided to you. And also I'm going to upload that specific topic in the lecture details portion that is attached in the portal in your portal as well. So if you look at the power now, so the power is basically getting reduced by 1 by 2. Initially it was 1 by 4, now it is 1 by 2, and the total power becomes AC square into x of t whole square. Now coming towards the specifications of this double sideband. So in a carrier suppressed system, mostly the power is reduced, as I've told you, because most of the power is lost in the transferring of the carrier. So normally there's minus 40 to minus 60 dB change in the power consumption, and also most of the power that was initially consumed by the carrier now goes or dedicated towards the sideband. So it means your sideband has been improved the efficiency or their content or their more energy for the sidebands. So the quality of the signal is basically improved. Similarly, there is another thing that you should also keep in mind, that normally such systems requires more complicated circuitry at the receiving end, because there is more complex demodulation on the receiving end sides because of the synchronization you have to do as you have nullified the effect of the carrier. So the transmitter hardware is more important and more complex as compared to the previous normal or conventional AM, commonly known as double sideband with carrier. And this is this kind of double sideband modulations with suppressed carrier is mostly suited when you are working and you are dealing with low frequencies, and there are some DC constants as well. So these are some specifications that you should keep in mind before actually specifying or going towards working with these kinds of systems. So this is the two types. The first one is, as I've told you, that the conventional AM, and second one is with suppressed carrier. Now both of these systems require to be have the transmission abilities. So for the AM transmitter, it is normally a non-linear element or some non-linear portion of the circuitry, like passive components and some of the transistors, etc. But it is often done where the message is superimposed on one of the active devices terminals, like gates, collector, drain, source. These are all the active device terminals, and you know what are active devices and what are passive devices. So these devices or these terminals of these devices are used in such transmitters. And because of these non-linear elements, this may require a tank circuit. Now what is a tank circuit? I have briefly explained you the tank circuit. That tank circuit is a combination of an inductor and a capacitor in parallel. So this is commonly known as a tank circuit. A tank circuit is a circuit which is basically used to generate a specific time or a specific frequency. And if you have generated the frequency, it means you are generating a clock, and that clock is used for synchronization, which makes it more difficult to receive and to send at the same time or at a different time, because synchronization is required while you are using these kind of elements like trunk circuits or transistors or any active or passive devices. So this is the graph of this AM. You see that this is your baseband signal or the message signal M of t, and the lower portion is basically your carrier. This thing is your carrier, and this is that nonlinear device that you are basically putting in, so that you have to basically do all your filtration portion, and after the filtration one carrier will be eliminated, and that voltage will be you receive, that will be your output voltage. You can see this V out will be equal to A1 V in plus A2 V into square. So this is the equation for the output of the such system, and the derivation is over here. You can also find this equation in your book as well. I have taken that the whole equation from your book, and this is a graph showing you the proper working of this AM with suppressed carrier, or you can you can also call it double side band with suppressed carrier. You can see that there is no carrier involved in this. So this is an example for the amplitude modulation modulator, that how this modulator actually works. So you can see that this is your actual X of t, and this is your carrier, and this is the input that you have generated after the modulation. And at the receiving end side, you can see that this is the tank circuit which I was talking about. This is a inductor, capacitor and inductor with in parallel connection, also with a resistor that is also commonly known as a pull-up resistor, you can call it, but not always this is a kind of pull-up resistor. Normally this is the LC circuit that is in parallel. And the first picture showing you the major concept, and the second picture is basically the practical circuit that is implemented. So you note that in this B diagram, the message signal and the carrier source are superimposed onto the gateway circuitry, that is this kind of circuitry. So this will be the complete message that is basically modulated. So there are several modulators or basically transmitters that are available in the market if you want to use this double side band. And due to the technological limitations, practical DSB systems are rarely implemented because these are a much complex system, and their efficiency is not that much good as compared to other systems that we will be learning in the coming slides. So the most of the popular modulators are known as basically balanced modulators, ring modulators, and other there are devices that are nonlinear devices we have which we have talked about. So this is a block diagram of this balanced modulator. You can see that both of these modulators, there are two modulators in which we have provided both the same with the same carrier, and in one of the output there is input was plus 1 by 2 of xt, and the second one was minus 1 by 2 of xt, and the only difference is of the sign, and in the last you get the actual equation that you actually transmit through the medium. But this diagram is only for the showing you the working principles of this balanced modulator. These are not practically implemented, and if they are practically implemented, the only use of nonlinear devices such as a diode, a list of diodes that is known as diode arrays. So the second type which we discussed is basically the ring modulator for this generation of this double side band. So you can see that in this kind of modulation you basically are using a kind of bridge circuit or a ring circuit of diodes, and this carrier is provided to both of these coils, this coil as well as this coil, and with the use of a transformer you can basically transmitting your signal to the final output, and this is then there is a use of band pass filter, and as I've told you, you have basically a specified amount of frequency which you allow, and there is a specified the rest of frequencies will be blocked. So you will get the final X of C over here. Now coming towards the second type, that is known as single sideband modulation or SSB. So if I want to explain you that SSB in a very simple way, so we are going towards more suppression of the sidebands. Now we have in DSB we suppressed only the carrier. In the SSB we also suppress one sideband to basically conserve more energy, to prevent the loss of more energy, and we only focus on one sideband so that in the information that we want to transmit has highest quality with the lowest power. So there is why we use the single sideband. And in the double sideband, if you remember, on normally the AM there was the bandwidth requirement which was of 2 FW, or the twice of the total message bandwidth. In the SSB, the total requirement of bandwidth is basically reduced, because instead of transmitting both of the sides, this side and this side, you only are transmitting one side and ignoring the other sidebands. You are only trying to basically transmit the upper sideband or only the lower sidebands. Now we will also discuss that how you can decide that which sideband you want to cancel out and which sideband you want to basically contribute to that in the information. So there are several types of this SSB based upon the you can say cancellation of or rejection of the sideband. The first one is known as lower sideband and or LSSB or simply LSB, and the second one is basically upper sideband or USSB or commonly known as USB. So the question comes here that which factors are the one that decides whether which side to choose, upper sideband or lower sideband. So there are several things that are involved. The first one is conventional and pure assignment. Convention means that what things are going on in the convention, and the pure assignment means what clients have asked you. If the client has wanted the upper sideband, so you have to set your system in such a way that you are cancelling the lower sideband and only allowing the upper sideband to transmit. And if the client has asked you to transmit the lower sideband, so you have to nullify the effect of the upper sideband. So the second thing is the technological considerations. So now due to the advancements of the technology in several things, you are basically have alternate paths. So this was the reason, this is the reason which was a major factor 10 years ago, but now there's the due to the advancements in technology, and for example there was a concept that you cannot transmit you cannot use 4G at lower frequencies, but due to the different methodologies and advancements in the technological methods and research, now people are basically actually trying to different companies are there who basically try or basically they have implemented such systems which use 4G at lower frequencies. So technological considerations are there, but not that of much impact. The major impact is the pure assignment and the conventional methodology. So neither USSB or LSSB is inherently better than the other. They both are the same, just the things that matter is the parameters or the environment. So both have the same properties. If the channel is not good for upper sideband and you see that there is a specific frequency that is cancelling the upper sideband, and due to the environmental hazards, or you can say the weather conditions, or the any of the environmental reasons, so you can also use the other sideband, and you can ask your client that that other sideband had some difficulty or error connections, or in the channel there was a lot of errors and corruption. So that is why we are going to shift our sidebands to a lower sideband, and the vice versa is going on. So this is totally a discussionable topic. I will discuss you in the class as well in detail. Now coming towards the equation of the single sideband. So this, if you see the equation, so you will this is a transform, just like you have. I have a hope that you have learned about ABCD transformation, Laplace transformation, and this is also a kind of transformation. We will be discussing that in the class, inshallah, because this is a separate topic of Hilbert transform. But just for your information, I have just mentioned it over here, so that you have the if you if not able to understand this transform by your own, you have the question in mind, and so that you can ask me in the class, and I will give you a bonus marks if you ask me about the Hilbert transform in the class as well. So you just have to ask me and you will get a bonus mark. So the in phase and the quadrature components are defined as this x of t, and this is the I component, and this is the q component. This is the two components. The first one is in phase and the second one is quadrature component. So the first one is in phase and the second one is the quadrature component. And the envelope of this single sideband turns out to be 1 by 2 of the amplitude of the carrier into the square root of the matches signal plus the Hilbert transform of that system. So if you see the spectrum of the single sideband, you can see that if you recall the previous DSB, there was such a system. Now you have basically cancelled this sideband, so you are only focusing on one sideband. So this is known as SSB, and this first one was, you can see that in this scenario you have basically cancelled this sideband, so it was upper sideband, and in this diagram in C you have cancelled the right upper sideband, so it is basically LSB or left sideband or lower sideband. And the first diagram was basically generation of SSB from the DSB. You get the DSB signal and then you apply a single sideband carrier and you get a single sideband. It is nothing but just a filter in front of a DSB. So in just applying a simple filter, you can reduce a small portion of power that was there earlier. So there are two methodologies. The first method is the filter method, which is commonly in use nowadays, and it also use a Q filter, the quality filter or the high quality filter, to suppress one of the sidebands. And there is another method that is known as the phase method, and in this kind of method you should basically shift the sidebands using a phase shift method to cancel one of the effect. So there are several things that you can use, but this mostly costs you much of the components, and this method is now more in use. So it is good to understand both of them. Now coming to the last type or the last category of this AM, the last one is known as VSB or vestigial sideband. So I have told you that in SSB the outcome is something like this. You have to basically cancel one of the filter and you filter out one of the sideband. Let's say you have cancelled this sideband, but most of the time it is not possible to filter at exact point. You can see this is not always the case. Ideally it is not possible or ideal to cut the frequency, or the filter is performing at such a sharp cutting edge. So their systems is not the perfect. There is not perfect filtration. Practically in SSB systems there are filters that are imperfect, and these imperfect filters are basically, we are termed as, this filtration is known as vestigial sideband. So VSB allows the messages from the lower frequency or the DC content as well. For example, let's say if you know that let me change my color or the marker of the color. If you know that the filter is not going to cut the frequency at this point, and you know that the filter is going to cut something like this information will be lost because of the filtration. So you know that this is the exact replica of this upper sideband, so you allow this portion of frequency to pass through it. So you design your filter in such a way that you basically cut the filter at this point, so that this curve will go like this. This information will be lost, but you can gain this information because you have allowed it over here. So this type of sidebands with the filtration process is known as vestigial sideband. Instead of going to the exactly at that point, instead of cutting the or filtering the your information at exact that point, you basically shift that signal or filtration process at some early time, so that some of the portion in the lower sideband is allowed, and you get that information which will be lost in the coming filtration process. So here I have given you a brief derivation for the you can see that double sideband with carrier suppressed, in which you have all the derivation over here, and this is just for your personal practice purposes. If you want to practice this equations, you can also get it. I have taken these images specifically for you. So let us summarize today's topic. There are two things. The first one is amplitude modulation, and the second one is their types. So most of the time, amplitude modulation is a vast term, is a generic term, and it is commonly known as double sideband with carrier. And this AM is known as double sideband with carrier. And if you talk about the more modification of this AM, you can call it DSB with suppressed carrier, or you can also do a SSB, that is a further advancement of this DSB, and you can also do a VSB, that is a further advancement or modification in the VSB. So you see that it is a linear you can say custom or a tradition, that you basically take the previous and apply some modification, then you take some previous input and apply some modification, and then you take this SSB and apply some modification, and you get this VSB. So this is a continuous cycle that which you can use while you are dealing with the amplitude modulation. So this was all about the amplitude modulation and its types. In the coming lecture, I hope we are going to discuss about the other topics that are of modulation, such as frequency modulation or phase modulation, commonly known as angle modulation. So we will be starting angle modulation in the coming class. If you have any questions or any doubts that are remain in your mind, you have to write it down on a paper so that you can ask me tomorrow in the class. I'll see you in the class. I hope that you bring some good questions along with you, because you know that the more you ask, the more you learn. I'll see you in the class. Thank you very much. Allah Hafiz.